So it's saying we have an electric field outside an infinite line that runs along the z-axis. And this is already done in one of the exercises in your book or the problems. The electric field is 2 lambda, with lambda being the linear charge density, how much charge is on the wire per unit length, 4 pi epsilon. S. So Griffith uses S for cylindrical coordinates. It's the distance from the axis of the cylinder. Okay, so this is derived in one of the problems, and it's fairly simple to do it. And the first question is, find the divergence of E, the E field, for S greater than 0. Right? So you're trying to find DE. Oops. Oh, this pad keeps on quitting on us. Oh no, don't do that again. Oh, this is annoying. What's this? Second, let me see, what was the... Open it. Electrodynamics. Oh, this is so annoying when it's doing that. Okay, yeah, so back to the question. So this is the electric field, right? A distance s away from the axis of a cylinder. This is in spherical coordinates. And the question is asking for the divergence of E. The divergence of E for s greater than 0. Okay. Now, of course, this is in cylindrical coordinates, yeah? Yeah, if you go to the back cover of your book, it tells you what the divergence in cylindrical coordinates are. I think it's page 595 or 596, something like that. Yeah, something like that. So yeah, it has it in cylindrical coordinates, the divergence, right? The divergence of E. Okay, whatever, either way, is 1 over S d over ds SES, right? This is straight from the definition of the divergence, where V in this case is E, because we're talking about the electric field, plus 1 over S dE phi, the phi component. This was the S component, over d phi plus dEz over dz. Okay, well, clearly the electric field does not have any phi dependence, so the derivative would be 0. And also it doesn't have any z dependence, So the derivative is also 0. There's only an s dependence, right? So then this becomes a straightforward problem. This is 1 over s d over ds. S and es is just 2 lambda over 4 pi epsilon, right, over s. And so here, right, because that's the s component, is 2 lambda over 4 pi epsilon s. So you can see that s cancels with s. And this whole thing that remains is a constant here. So what's d over ds of a constant? 0. Right? So you get 1 over s times 0. So the divergence of E turns out to be 0 along the S. Right? Questions on this manipulation? Okay, good. You got that? Okay, great. So now let's go to the second part. What does it say? Right. Okay, good. And yeah. So electric flux, if you remember, that's just the integral of EdA. How much electric field is fluxing out of an area. Yeah, and this is a closed integral on a surface or in an area. Yeah, this is the flux. No? And we have a Gaussian cylinder centered around the z-axis. So length L, radius A. So why don't we center it at 0, 0? Let me make this a little bit smaller. Right? You get the idea here. So this is our cylinder. And we want the flux, yeah? Now we could do this in 2 different ways. We could do it using direct integration, or we can apply Gauss's law. right? And the length of this cylinder is L, and the radius is A. Okay, and of course this is following the first question. And here we have z-axis, x, y, and we have a sheet of charge. I mean line of charge. Okay. Yeah. So you know, if this is a Gaussian surface, then Gauss's law says the flux is just equal to Q enclosed over epsilon. Q enclosed in the Gaussian surface means how much charge is here, right? Because we are enclosing the infinite line that runs along the z-axis. Yeah. And how much will be enclosed? Well, if this has a surface charge density lambda, then it's coulombs per meter times the length of the wire, which is the length of the Gaussian surface, which is the length of the cylinder, which is L. So the flux will be lambda L over epsilon. So Q enclosed is lambda L over epsilon. So this would be the flux. This is using Gauss's law. Yeah? If you want to use direct integration, so this is the first method. Let's do it using direct integration, right? We said that the flux is integral of EdA, right? On the surface. Okay, well, we said in part A that the E was 2 lambda over 4 pi epsilon, right? It's given. So this is 2 lambda over 4 pi epsilon S in the S dot dA, right? Now dA, okay. Look, so over the area of, there's 3 parts to the area of this cylinder. If you are here on the top, let's do this in red. If you are on top or the bottom, the area vector is perpendicular to the surface. So it's either pointing down, right? Or pointing up, right? This would be the area vector. Let's call it normal vector n. Now, the electric field has components of S. S points from the axis outside. So this is unit vector S. You can see that on top of the cylinder and the bottom of the cylinder, n dot S is equal 0. Why? Because the angle is 90 degrees. The dot product is magnitude the first, magnitude the second. And these are 1 because they're unit vectors, cosine 90. So n dot S equals 0. So there's no contribution to this integral from top and the bottom. No? Okay, so now the only thing that survives are the sides. So on the sides, right, dA points in the same direction as ds, as you can see here on the sides right here. So they point in the same direction, and the angle between them is 0. So here we will get a contribution. So this is times dA also in this, or I can take the magnitude of dA in this, right? Closed integral. Because the area vector is normal to the area. On top and the bottom, the normal vector is coming out in the positive z and negative z directions, and the electric field vector is coming radially outwards in the s direction. So they're perpendicular to each other, which means their dot product is 0. Yeah. Yeah. So this just becomes, so if I were to continue here, 2 lambda, right, over 4 pi epsilon 1 over s. Now, what's dA in cylindrical coordinates? Yeah, it's just it's just taking an elemental area, a chunk, and going around with it, right, on the surface of the cylinder. So you have you have dA. I mean, the area of the cylinder is 2 pi r times L, or s times L, right? So dA will just become A on the surface of the cylinder. And so we can remove the, right? Because all we have now is integral of dA. Okay, so this becomes 2 lambda over 4 pi epsilon 1 over s. dA is 2 pi SL. Because, by the way, 2 pi is coming from d phi 0 to 2 pi, which gets you 2 pi on the dA. Yeah. And s is coming, ds from 0 to s. So that gets you an s. Yeah. So s crosses out ds, right? You get 4 pi crosses with, because you have a 2 here, with 4 pi. And the flux will be lambda L over epsilon. Exactly the same answer we got from Gauss's law. Lambda L over epsilon. So you can see that using Gauss's law is much more efficient and much quicker than actually having to do integrations. R is S. Yeah, I know. That's why ds became S, because you're going from here to here. This is S. Hmm? Yeah, S is constant. Right. So that's why the area turned out to be 2 pi SL.